We'll talk now about graded potentials. Graded potentials. So graded potentials are, now we said our membrane channels could be ligand gated or voltage gated. Now it's important to note in graded potentials this is change in membrane potentials, where first we are talking here when we talk about graded potentials, we are dealing with ligand gated channels. And the ligand could be neurotransmitter, acetylcholine, for example. And then now the strength of the depolarization of the stimulus, of the response, depends actually on the strength of the response depends on the strength of the stimulus. It's very important. So we said we have ligand gated channels, and the strength of the response depends on the stimulus. So what happens when you have a stimulus that hits you have a ligand that binds to when you have a stimulus here on your membrane. Remember, we're talking about neurons here, and these ligand graded potentials mainly occur in skeletal muscles, in cardiac muscles, and in dendrites and also cell bodies of neurons. So once there is a strong stimulus, you have a ligand that binds to our sodium channels. Okay, ligand that binds to our sodium channels, and then when it binds to our sodium channels, we have depolarization. We have a depolarization of the membrane. Now this depolarization, the strength of the depolarization will depend on the strength of the stimulus. The higher the stimulus, the higher the concentration of the ligand, the higher the stimulus. You can see here, this is a strong stimulus in red, which produces a stronger membrane depolarization, while a weaker stimulus produces a weaker response. So we have the depolarization of the membrane, which depends on the size of the stimulus. And also we can see here the further we are going away from the focal point where the stimulus was, we see that the response is decreasing. Yes, the further away we go from, because this is where the stimulus is acting directly on here, the stimulus is maximum, and the further away we go from this point, the more we see a decrease in the response. So these are characteristics of graded potentials. There is a decrease in response with distance away from the stimulus, and the response, strength of the response depends on the strength of the stimulus. Okay? Yes, graded potentials. So that is it. We move. So now we are going to talk about action potentials. Yes, now we are in action potentials. Now action potentials, contrarily to graded potentials, we have voltage gated sodium channels. Yes, it means they don't respond to ligands, but they respond to voltage, changes in voltages, sodium and potassium channels. And now these channels, okay, sorry, they are voltage gated. Now, once there is a stimulus in the cell or in the neuron, since we are talking about neurons, and okay, these action potentials actually happen in the axons of neurons. Remember, we said graded potentials happen in the dendrites and other muscles, skeletal muscles, while action potentials happen in the axon of the cell, of the neuron. So once there is a stimulus, it causes a small rise in the voltage. So a stimulus will change the voltage of the voltage of the membrane, across the membrane, and This change in voltage leads to opening of sodium and potassium channels. Yes, this change in voltage leads to opening of sodium and potassium channels. Remember, we said they are voltage sensitive, voltage gated. So once here we can see this is closed. So once there is a stimulus, the sodium channels open and potassium channels also open. But now the marked difference is potassium channels open very slowly compared to sodium channels. So it means once there is opening of sodium channels open way before the potassium channels open. So as when the sodium channels open, what happens is sodium influxes inside. Sodium influxes inside. With this influx, it depolarizes the membrane, and when it reaches at certain points, potassium channels fully open. You can see now here, when sodium channels are open, here at this stage, potassium channels are open, and we see here, take note, this the sodium channels are inactivated. Remember, they are inactivated, not closed. They are inactivated. Here in the first step, the sodium channels are closed, but here they are inactivated. There is a difference because here they cannot be stimulated even if there is a stimulus. Here the channels can open, here they cannot open because they are inactive and not closed. They are inactive. So potassium channels are open here, and potassium rushes outside and repolarizes our membranes. And then here everything closes back. Everything closes. And now it's important to note now this period where the sodium channels are inactive is called the refractory period, and it's very important in the neuron in transmission of impulses. It's called the refractory period. So refractory period is the period where sodium channels are inactive. Okay, so this is the timeline of events that happen during the action potential. So let's explain quickly. So in stage 1 here, the resting membrane potential, both sodium and potassium channels are closed. So now here we see we have various stimuli, and at the beginning of this stimuli we have opening of small ligand gated channels, and they start changing the membrane potential. And what happens if this membrane potential does not reach? There is a certain threshold here. This threshold in the axons. Yes. If this change does not arrive at this threshold, there is no action potential. And what happens if once the change in membrane reaches this threshold, there is an action potential? All these events occur. So either the amount of the action potential does not depend on the stimulus. Once it reaches the threshold, it is the same response. An action potential gives the same response once the stimulus reaches the threshold, once the change in membrane potential reaches the threshold value. And generally speaking, the threshold value there should be a threshold change of 15 millivolts. Yes, in membrane potential. That's generally speaking, there should be a change in 15 millivolts. So once the change does not reach the threshold, there is no action potential. So we call it subthreshold stimuli, and this is called the all or nothing law of nervous transmission. Is the all or nothing law of axonal transmission. If we want to be more precise, the all or nothing law. So stage 1, both are closed. Stage 2, once the threshold has been surpassed, see sodium channels open quickly than the potassium channels. So once sodium channels are open, there is an overshoot. You can see here, it's open and it goes right up, generally up even more than to 60 millivolts. So once these sodium channels are open, there is this overshoot. And on the third stage, stage 3, our sodium channels become inactivated. Sodium channels become inactivated and our potassium channels are open. Once potassium channels open, potassium flows inside. potassium flows outside. Sorry, potassium flows outside and repolarizes the membrane. And generally what we see here is that at stage 4, the potassium channels, and here remember this is the refractory period where the potassium sodium channels are closed, and here in the refractory period you cannot stimulate the sodium channels. Yes, so refractory period, and then stage 4, sodium channel closes, potassium channels kind of slow to close. So what happens in stage 4 is that the cell hyperpolarizes because potassium channels are still open. They are closing, but they are slow. So the membrane hyperpolarizes and goes to a membrane that is even much more negative than what it was before. Then stage 5, both channels are closed. After both of them close, we have the sodium potassium ATPase, which reverses the ions back to their initial state. Because remember, after all of these, potassium is high outside and sodium is high inside. So we need now the sodium potassium ATPase to reverse, to send, to pump sodium outside and pump potassium inside, and come back to our membrane potential in stage 5. So that is it for the action potential, and I hope there we have gotten some differences between graded potentials and action potentials. Now, when we saw the diagram here of a graded potential, we see that graded potential can transmit in both directions. When stimulus here, we see that there is depolarization on both sides. Okay, yes, on both sides of the channel. So depolarization is going both sides of the channel. That is not the same case in action potentials. Action potentials, there is depolarization only on one side. Now this is because of this refractory period here. Because once you have, once a sodium channel has reached this stage 4, it has reached its action potential, and then what is happening is there is kind of a ripple effect, a positive feedback. Once this is depolarizing, it is increasing the potential of the membrane, and so nearby membrane sends nearby voltage gated sodium ion channels sends that change and also open, and so there is increased depolarization across the membrane. But what happens is when the next sodium channel is opens, the previous one is in the refractory period, it cannot be stimulated. So it means that sodium ion channels cannot. So it means that once this one is inactivated for a certain time period, it cannot transmit an impulse. So the impulse can only go in one direction, because once it has transmitted an impulse, it is inactivated and sodium can no longer transmit. So once this sodium channel has transmitted an impulse, it is inactive for a certain period of time. So it causes that membrane action potential travel only in one direction. Thank you. very important.